Dear students, in the last few classes we talked about the development of quantum mechanics. We talked about that how quantum mechanics came into existence. There were certain experimental observations which could not be explained in the by the classical mechanics, so a new mechanics was developed, and it took from 1900 to 25-26 years, and then we came to the Schrodinger wave equations, which we have written as d square psi by dx square plus 8 pi square m by h square e minus v psi x is equal to 0. This equation is known to you. Earlier also you have done, but now we derived this equation, and what we did is that we changed this fx function, which was the function dependent on x, as psi. That's all. It's actually the classical mechanics equation. We modified the classical mechanics wave equation to the Broglie wave equation, nothing else. Okay. And the shortest form of this equation which we did was h psi is equal to e psi. This psi we say as wave function. In quantum mechanics, the whole idea is to know the system, and if you have to know the system, then the only property in quantum mechanics which you need to know is the wave function of the system. So for any system under observations, our goal is to find out wave function for the system, and we say wave function contains all the properties of the system. By all the properties, I mean, if you want to know the position, if you want to know the velocity, if you want to know the energy, if you want to know the momentum, if you want to know the angular momentum, then all kinds of physical variables which could be experimentally determined can be calculated from the wave functions also. Okay, so in order to do this, these calculations, there are certain rules framed by developers of the quantum mechanics, so which you have to always follow, and these rules are called postulates of quantum mechanics. So we will talk about there are 4 or 5 postulates, and we will talk about each one in details. Okay, let's go back. We will start with the postulates of quantum mechanics today. So postulates of quantum mechanics. These are rules. We will not talk about why it is so, and there is no answer for why, but as if because these are the fundamental rules which you have to follow always. If when you were a child, you were asked to write the A, and you were asked to write that this is A, and you got it that this is A. You never question why this is A, why not something else is A. Okay, so it is as basic as this one. That adhering to the postulates is as basic as to this one, that your A is this one, it cannot be anything else. Okay, so postulates are fundamental rules fundamental, unquestionable rules in the quantum mechanics. And the first postulate in quantum mechanics is about the wave function. And wave function is represented as, given a symbol psi, pronounced as psi, and this wave function is a function of coordinate x, y, z and time t. In some places you will find f, r1, r2, r3 and so on and t, where r1, r2, r3 are the coordinates of the system. Okay. So wave function has wave function is dependent on two different functions. One is the coordinate, another is time. Coordinate and time. If your system is one-dimensional system, then you can write psi is equal to a function of x and t only, or psi is a function of r and t only, where r is the coordinate, t is the time, x is coordinate and t is the time. Okay. We already split it into two different functions when we did the derivations of Schrodinger wave equation. So this wave functions, if I write this function as psi is a function of x only, then we say this is a time independent wave function. Okay. And if you write this one psi xtrt, it is called time dependent wave functions. We have only come across with the time time dependent function if you have to find out a physical variables which is time dependent. In most of the part of this course, we will be talking about time independent wave functions, where the wave function will depend only upon the coordinates. Maybe if you have a single one-dimensional system, then it will be x dependent, or if it is a three-dimensional system, then it will be x, y and z dependent functions. So we will be talking about for 1D, and if it is psi function of x, y and z, then we say it is for 3D systems. Okay. Now what this psi is? Psi is a function so what kind of function is this? It's a mathematical function. Sorry. Psi is a mathematical function. So what it should be? A mathematical function means psi could be anything, could be x square, is it so? Psi could be exponential, psi is equal to exponential kx, psi could be sine kx, a trigonometric function, an exponential function, anything. We say psi could be a real function, a real mathematical function, or an imaginary mathematical function, both. Okay. When we say imaginary functions, means the complex, a little bit of complex number you will have to do here, and if you have already done, it's good. So what you can write is, if z is equal to x plus iy, then this Z star is the complex conjugate which is given as minus I by, where this is called complex conjugate. Okay. So psi is a mathematical function. It could be real, it could be imaginary. If you have a function like this one, psi is equal to exponential kx, and if you plot this function, psi versus x, then you get a plot like this one. K1, K2 and K3. What does it mean? It means that K1 is it's an exponential function which is rising with increase in the x value. So the rise is very steep here. K3, it depends if K3 value is very high, where K is a real part, okay, real function. And if it is, so psi is equal to exponential minus kx also you can write, and if you plot it like this one, then there will be an exponential decrease of the function. So there will be an exponential decrease, exponential decay, and there will be exponential rise. Okay. So I could be a function like this one, okay, or psi could be x into exponential minus kx square, or psi could be x square into exponential minus kx square, and so on. Okay, you can have many different, you can write many different functions. Same way, if you have psi is equal to sine x, then you can plot this sine wave. All of you have done it like this one. Okay, so there is no at present at this stage we will not put any limit. I will say psi is a mathematical function only. What kind of mathematical function it should be? For knowing that, first we will see that what is the physical significance of psi. What we say is that psi in itself does not signify anything physically. Okay, so there is no physical significance of psi, but psi square gives probability density. Okay, so this interpretation is called Born interpretation. Psi is probability amplitude, we can say, and psi square is probability density. So what you can do is that you can multiply psi square with volume element, and what do you get? You get probability. So once you know the psi value, you can find out the probability. Okay. This is what is called Bond interpretation. Now if you write it, psi square d tau as the volume element, then this d tau is a three-dimensional volume element in Cartesian coordinate. What you can write is it is equal to dx dy into dz. Okay. So if I integrate this probability over whole space, and whole space we say by writing minus infinity to plus infinity, then this gives you the probability. Okay, because psi square d tau. If the function is not real, it is imaginary, then the same equation becomes psi star d tau from minus infinity to plus infinity. Okay. Now this gives you the probability, and this interpretation itself imposes certain restriction on the mathematical functions which could be, or which could be the wave function. And so all mathematical functions cannot be the wave functions. Now what I said you, that psi star d tau is probability, and probability has to be a finite value. It has to be a finite value. It means because system has to be somewhere if you are integrating over whole space, so it must be less than infinity, and if it has to be less than infinity, then this imposes the restriction that this integral must give you a finite value, and this is the first criteria for the wave functions, that wave function must be square integrable. So we say the first condition is wave function must be a square okay. So what does it tells you? It tells you that the Bond interpretation tells you that psi square gives the probability density, so you multiply it by volume, you will get the probability. And if the system is existing, then if you integrate this integral over whole space, then it must have a finite value, it cannot be infinite. And if it has to be infinite, it means the integral value of psi star d tau or psi square d tau, if it is real, then must have some finite value, and this finite value imposes the restriction that your wave function psi must be a square integrable. So in order to give you a finite probability value. Okay. And so The related thing is that psi, second condition for the wave function is that psi must be finite also. Because if you put psi is equal to infinity, the integral will also be infinite. That's not possible. Probability cannot be infinity. Okay, so psi must have finite value. What does it mean? It means that if you write psi is equal to x, where x is the variable, then this variable will go on increasing and psi will go on increasing and x will be infinite. X is infinite. Let me write it this. We say that at x is equal to infinity, psi will be infinity. So this cannot be a wave function. Psi is equal to x square. Here also the same thing. At x is equal to infinity, psi is infinity. So this is also not possible. This is also not acceptable. This is not also acceptable. Okay. Then we say psi is equal to exponential x. So this is again not acceptable. At x is equal to infinity, psi will be infinity. Okay. If I say psi is equal to exponential kx, this also is not possible. At x is equal to infinity, psi is infinity. So you can find many different such examples, and so that's why I plotted a graph between psi and x, and I showed you that an exponential function like this goes on. But if you have psi is equal to exponential minus kx, then this is an acceptable function because it's an exponential decrease. It will not go to infinity. Okay, so this will be acceptable function. Okay, your psi is equal to sin x is an acceptable function. You have seen the graph because it oscillates from one value to another value like this one. Okay, so it has a finite value for all values of x. For all values of x, sin x is finite. So it's an acceptable wave function. So the first restriction is it should be a square integrable and must be infinite. Second restriction must be infinite. Must not be infinite. Must not be infinite. Psi must be finite. Second restriction. Okay. Another implication of Born interpretation is this, that since psi star d tau gives you the probability, so the psi must be single valued also. Okay. The third implication of Born interpretation is that psi must be single valued also. Single valued. If I plot a graph of a function psi versus x and we get a curve like this one, then for all values of x you have only one value of psi. At x1 you have psi 1 value, at x2 you have psi 2 value, at x3 you have psi 3 value, and all these values are different. Okay, so at each point you get a different psi values, and this is the graph of a sine function. Okay, so but if you have a graph like this one of psi versus x, like this one, then for the same value of x, you have psi 1 value, you have psi 2 value, and you have psi 3 value. So we say this is a triple valued function. If you have a graph like this, psi versus x, then this is a two different values of psi you have, psi 1 and psi 2, so double valued function. And how it is an implication of Born interpretation? It's an implication of Born interpretation because if you have for the same value of x 2 or 3 values of psi, then you will have at the same point 2 or 3 different values of probability, which is again a absurd thing. At a particular x value, there should be only one probability, so the function should be single valued also. It must be single valued. But there is an exception to this one. Single valued function exception is when we talk about a spin function. Okay, and when we talk about electronic, when we talk about electronic spins, okay, which certainly will not be the part of this course. Okay, but psi must be, so in general, psi must be single valued, psi must be a square integrable, psi must be finite. Okay, what else? Okay. The next thing is that psi must be continuous also. Must be continuous also. Means if you have a function, sorry, this function is not a continuous. There is a break when the psi value is x1 and the psi value is x2. So such functions will not be or cannot be unacceptable functions. So psi must be why it should be continuous? Because if you have a sudden jump, then you will have a sudden probability jump also. For a very small values of change in the x, there will be a very sharp change in the probability, again which will be an absurd thing, which will not be good. Okay, which cannot be, because if at x is equal to say 1 nanometer or 1 angstrom, you have some probability, then at 1.1 angstrom, the probability cannot be very high or very low from this value. It should be change continuously. So this psi must be continuous also. Another criteria is that the first differential of wave function should also be continuous. And again, first differential will be the slope of the wave functions. So slope will be ddx of psi. And if you plot this, then this also should continuously vary. But this is valid only when there is not a very sharp difference in the potential at various small part. Exception is ill-behaved potential. I will talk about ill-behaved potential when I will talk about particle in a one-dimensional box. And if you have done into undergraduate courses, what you do in a one-dimensional box, you say that inside the box the potential is 0 and outside the box potential is infinity. So this is called an ill-behaved potential, because exactly at this point you jump from 0 to infinity. So in this case, at this point, at x is equal to 0 and x is equal to a, if you plot a wave function, then its differential will not be continuous. So the exception is ill-behaved potential here. So these 5 criteria, if any wave function fulfills, then we say that it is an acceptable wave function or it's a well-behaved function. The term which is used is acceptable wave function. It should be a square integrable, it should be finite, it should be single valued, it should be continuous, and the first differential should also be continuous if the potential is not ill-behaved potential. Okay. Any wave function which fulfills these 5 criteria is called a well-behaved function. So the first thing is that you must find a well-behaved wave function for the system. Okay. Now I said you that whenever you square, Born interpretation is that if you square this one, square the wave function, then you get the probability density, and if you integrate the square over the whole space, then this gives you the probability. So let's see what happens to this particular integral. Let's suppose if you have a function psi 1, it's minus infinity to plus infinity, okay, psi 1 star d tau. This should give you the probability. Now if you have a system like this, that your particle is present in a one-dimensional box, for example, I am taking 1D box, and the wave function is psi, then for this relationship you can write psi d tau from x is equal to 0 to x is equal to a. So your minus infinity will be 0 and plus infinity will be a. And since the particle is present, so we say its value should be equal to 1, because the maximum value of the probability could be 1. Okay. So whenever you have a wave function, you must see that its square integrated over whole space should give a value of 1. Then only you are sure that the particle is present within the boundary. Okay. So we can write this as psi star d tau from minus infinity to plus infinity is equal to 1, or if it is a one-dimensional system, then minus infinity to plus infinity psi star dx is equal to 1. If a wave function psi fulfills this criteria, we say the wave function is normalized. This is called Normalization condition. All wave functions, if you have a system, you need to know the wave function. If you have a system, you need to know the wave function for this one. And if you find out the wave function psi, then you should ensure that the wave function is normalized. Normalize the wave function. In order to get the meaningful values of the physical variables. Why normalization is important? Because this ensures that your particle is present within the boundary. Okay, if you want to play a football match, then you ensure that the ball is within the boundary, then only you play. So the same thing is here, that your particle must be within the boundary, then only you can find out the physical variables for the system. Otherwise you cannot. So the first thing is to find out the wave function, and the next step is to normalize the wave function if it is unnormalized. So how to normalize a wave function?